Good morning, students. Welcome back in lecture number 4, viscosity for BSc first year physics students. So in this lecture we are going to discuss about Bernoulli's theorem, Bernoulli's formula, proof of Bernoulli's theorem, its mathematical equation, applications of viscosity, and so on. Now let us discuss the concept of viscosity about Bernoulli's theorem. Statement of Bernoulli's theorem is that the total mechanical energy of the moving fluid, we are related, this chapter related to the fluid. So every moving fluid possesses energy. The total mechanical energy of the moving fluid, comprising the gravitational potential energy of elevation, the energy associated with the fluid pressure, and the kinetic energy of the fluid motion remains constant. Very simple and very important theorem, Bernoulli's theorem for exam point of view, and very easy to understand. The total mechanical energy of the moving fluid body, comprising gravitational potential energy of elevation, the energy associated with the fluid pressure, and the kinetic energy on account of its motion remains constant. Total energy remains constant. In short, you remember. The Bernoulli's equation formula in relation between pressure, kinetic energy, and gravitational potential energy of a fluid in a container, it is nothing but P plus half rho V square plus PGH, rho GH equal to constant. Where you know P is what? Pressure exerted by the fluid. V is velocity of the fluid. Rho is density of the fluid. H is height of the container. In this way, total energy of the fluid is constant. From this mathematical expression, it is clear that E plus kinetic energy plus potential energy remains constant. Now let us turn towards its proof. In case of Bernoulli's theorem, we have seen that total energy, mechanical energy, remains constant. How it is to be proved? That proof we discuss now. See here figure, carefully observe this figure. What are these? These are the what? Parallel lines of the flow of the fluid. Yes, again carefully observe this figure. In this figure, V1 and V2 shows the velocities of the fluid at points Q and R respectively. In previous lecture, we have shown tangent at a particular point to this curve or to these parallel layers gives the velocity of the fluid. So in this way, V1 is the velocity of the fluid at Q and V2 is the velocity of the fluid at R. Here area of the fluid at Q is more, A1 suppose, and here A2 was area at R, it is smaller than A1. From this figure, it is clear that here pipe is more large in size and area is more, and here area of cross section of the pipe is what? Less, so that A1 is greater than A2. Here pressure is P1 at this area, and pressure is what? Here we have taken for example, let P2 be the pressure at this area, smaller area. Then naturally, you know, whenever large is the area, pressure is less. Smaller is the area, pressure is more. We have seen here smaller area, larger the velocity. Larger the area, smaller the velocity. All these things we have seen in previous lecture. Now how to prove this? Bernoulli's theorem we discuss now. Consider a fluid of negligible viscosity moving with a streamline flow, as shown in figure. What we are going to consider? A fluid having negligible viscosity, and its flow is what we have considered? A streamline flow. Again, let the velocity, pressure and area of the fluid be V1, P1 and A1 at point Q. V1, P1 and A1 at point Q. Velocity, pressure and area. In the same way, velocity, pressure and area at R, B, V2, P2 and A2 respectively. A2. Let the volume bounded by Q and R move to S and T. Volume bounded at Q and R move to S and T. S and T points are shown here. S point is here, T point is here. Volume moves from Q to S and R to T. Suppose QS is L1 and RT is what? L2. If the fluid is incompressible, then A1L1 is equal to A2L2. This formula you remember. If the fluid is incompressible, but practically no fluid is incompressible. So we are going to consider a negligible viscosity. Okay. Now let us turn. Then work done for the pressure difference per unit volume is nothing but gain in kinetic energy per unit volume plus gain in potential energy per unit volume. This is nothing but work done by the pressure difference per unit volume. Now work done is nothing but force into displacement of the body along the direction of the force. Then it is nothing but P into volume, pressure into volume. The net work done per unit volume is given by P1 minus P2. Kinetic energy per unit volume is nothing but half mv square. It is equal to half v rho v square. Is equal to half rho v square. Where when v is equal to 1, I mean for unit volume, v is considered to be 1, then kinetic energy is nothing but half rho v square. V is what? Velocity. And this v is volume. So for unit volume, v is equal to 1, then kinetic energy per unit volume is nothing but half rho v square. Here it is shown. Kinetic energy gained per unit volume is equal to half rho v2 square minus v1 square. Potential gained per unit volume is rho g h2 minus h1, where h1 and h2 are the heights of Q and R above the same reference level. Here if you will figure, you see carefully figure also. Then you will come to know. Here Q and R. These are the levels. Suppose this is the reference level. Suppose this is the reference level, for example. This is from this reference level, Q is at height what? And this is at height, another height. H1 and H2 be the heights of the points Q and R from a certain reference levels. H1 and H2 are the heights of Q and R respectively. Then P1 minus P2 is equal to half rho V1 square minus V2 square and this. So minus P1 is to be taken to this side, it becomes plus. So in this way, by rearranging the terms, negative terms to the left, it becomes positive, and positive negative positive to the left becomes positive. Here minus P2 becomes plus P2 here, minus H1 becomes plus H1. Therefore, P plus half rho V square plus rho GH is constant. So in this way, Bernoulli's theorem you can easily prove. For a horizontal tube, H1 is equal to H2. Suppose tube is not like this. It is exactly horizontal. I mean both the heights, height at P, height at Q, both are equal from a certain reference level. In case of horizontal tube, it happens. What? Horizontal tube in the sense, it is every point of the tube is equidistant from the reference level. I mean it is at a height of certain level. So in horizontal tube, H1 is equal to H2. Therefore we have P plus half rho V square is a constant. No difference in the heights of the points. So this is about Bernoulli's theorem. This is the Bernoulli's theorem. You can see that if there is an increase in velocity, there must be decrease in pressure. Velocity increases, pressure decreases, and vice versa. I mean, velocity decreases, pressure increases. But no fluid is totally incompressible. Already I have told you, no fluid in nature is totally incompressible. It is just some quantity, it may be, it is compressible. No doubt it is slightly compressible, but not totally incompressible. But in practice, the general qualitative assumptions still hold for real fluids. But while doing the proof, we should consider what? The incompressible fluid. I mean, we have to assume that the fluid is incompressible. I mean, whenever we are going to achieve a target, we have to keep the target of a real atom, ideal atom. For example, suppose you are going to prepare a machine. So we should prepare a machine. Our aim should be that it should be like ideal one. So we consider that the machine prepared is what? Ideal. But no machine is prepared in nature, it is ideal. That's why we say that we are considering the ideal machine. We are approaching towards the ideal characteristics of a particular machine. In the same way, in case of fluid, we are considering in while proving the Bernoulli's theorem, we assume that the fluid flowing through the pipe is what? Incompressible. Now, what are the applications of viscosity? So what are the benefits of viscosity? What is the use of viscosity? What is the purpose of using viscosity? Transparent and storing facility. Transparent and storing facilities for fluids, that is pipes, tanks, etc. As it is a viscous, that's why we can store it. Bitumen used for road construction. Designing of the shear line and or any other pipe flow, viscosity play an important role in finding out its flow behavior. Drilling for oil and gas requires sensitive viscosity. Drilling viscosity plays very important in case of drilling of oil as well as gas. To maintain the performance of a machine and automobiles by determining the thickness of lubricating or motor. See, periodically we have to replace what? The engine oil, brake oil. We have to grease the certain moving parts of the automobile. The reason behind it is what? Because of the viscous nature, what happens? Life of engine increases. Not only life of the engine increases, but it maintains smoothness of the engine. So this is the benefit of viscosity. If suppose liquid is not viscous in nature, then what happens? It will not maintain the temperature of the engine. Temperature of the engine goes higher and higher, and one thing happens. What? Life of the engine decreases. So viscosity plays very important role in case of maintaining the performance of machine and automobiles by determining the thickness of lubricating oil or motor. How oil thick, how oil thin, it determines the viscosity of the liquid or oil, and it is useful for the better performance of the machines as well as automobiles. So in this way, we have completed this fourth lecture also.